Okay then. So today's lecture is going to be about transient stimuli and excess carrier concentrations as a result of transient stimuli. And then we'll get into a more unsteady state stimuli. We'll talk about quasi Fermi-levels, photoconductors, and then we'll get into the continuity equation and diffusion. I think this is a good slide to start some of our review on. So last time in class, we talked about various types of stimuli in electronics. In your circuits class, you're familiar with these three types. Equilibrium is when you have a circuit and you don't apply any voltage or current to it, so that's considered no stimuli. When we're talking about this class, for the context of this chapter, we're not talking about applying a voltage or a current to it. We are talking about shining a light on a semiconductor. That is our stimulus. And as you know, the light generates excess carriers, generates electron hole pairs.
So just the light, not the temperature, increasing the temperature, it will not count?
This module talks specifically about light. So it's a good question. The question is, can you do with temperature also? Increasing temperature does increase carrier generation and recombination. It does generate more carriers, but we're focused on light. The reason we're using light here is because with light, we can deliver all three types of stimuli. We can deliver equilibrium stimuli, which is no light. We can deliver steady state stimuli, which is just a steady stream of light. And then we can also deliver transient stimuli, which is a sharp pulse of light. Harder to do that with temperature. Okay, that's why we're using light here. So equilibrium, again, no external excitation, no net current, carrier concentrations don't change with time. Steady state means you're shining a steady state light. All processes are constant and balanced by opposing processes. So in this case, generation of carriers is balanced by recombination. The two processes are in equilibrium with each other. And so there's a steady state carrier concentration. We'll talk about that. And then there's a transient case. The transient case is when you apply a very quick pulse of light. And in that case, the carrier concentrations will change with time. You know, you'll get a sudden increase in carrier concentration when you put that pulse in, and then those carrier concentrations will die out with time. Does anyone remember the definition that we talked about last time? What is that term that we use to describe how fast the carriers disappear? Lifetime. Yeah, exactly. You got it. The carrier lifetime. And so there's a carrier lifetime for electrons, and there's a carrier lifetimes for holes. What determines the carrier lifetime? Or let me be more specific. How does carrier lifetime change with doping, and why? If you increase the doping, then what happens to the lifetime? Nope. It's actually the other way around. When you increase the doping, the carrier lifetime decreases. Why do you think that might be the case?
There's more chance to recombine and die. Exactly.
If there's a lot of electrons in holes, then there's a higher probability that they're going to meet each other and annihilate one another. So that's why the carrier lifetime goes down. The carrier lifetime is the average time the carrier between generation and recombination events. Okay, so that carrier lifetime is very important when we talk about transient stimuli. All right. So this chart just summarizes what we talked about. We started talking about steady state excess carrier concentration last time. So steady state stimulus, and there's a simple equation that describes the excess carrier concentration. Just to note here, sigma n is the excess carrier concentration. A reminder on notation, because this notation always flubs people up. So N0 is before light. So this is the baseline. And then sigma n is the excess due to light. And then n, which is equal to n0 plus sigma n, this is the total. the total electron concentration. And the same goes for holes. Okay, so the sigma n here, the sigma n is, oops, there we go. Sigma n is equal to tau n times GOP. The tau n is the carrier lifetime, and the GOP is the generation rate of these electron hole pairs. The generation rate will generally be given to you, and the carrier lifetime is also a property of the material. Longer carrier lifetime, higher generation rate will both increase your steady state carrier concentration. That makes sense because the larger the lifetime, that means the longer it takes for a carrier to recombine, and therefore the higher the excess carrier concentrations you would have. All right. So we did an example of steady state generation and recombination at the end of class last time, and so I won't go over that. Today we'll jump right into transient stimuli. All right, so in the case of transient stimuli, this is what happens. So carrier lifetime can be understood in this simple example. So we see where we are illuminating a material with light. So the first thing that happens is we establish a steady state carrier concentration at t is less than 0. Then at t equals 0, we turn it off. And now we're looking at the time response of the semiconductor material. Okay, so at time is less than 0, the light is on. Okay, and that light is such that we're generating carriers. So the carriers are shown here. So these are the excess carriers. Notice that I have them in pairs, blue and white. The blue stands for the electrons and the white stands for holes. They're generated in pairs. And when you turn the light on, an equilibrium is rapidly established. Very, very quickly it's established. And so you can find the excess carrier concentration using these equations. Okay, so you have excess carrier concentration now. At time equals 0, what we're going to do is we're going to turn off the light, and then we're going to see what happens to the carriers. I think we went over this in class last time. Initially, when you turn off the light, the carriers, the electrons and holes are still, the excess electrons and holes are still present because they can't disappear instantaneously. They decay with time, right? Having to do with the carrier lifetime. Right, so it turns out that the excess carrier concentration is an exponential function, and so they decay like this. They just they disappear when electrons and holes. This isn't a precise example because the electrons and holes could be moving. You know, they could be diffusing, they could be moving due to drift, they could be moving to the left and right. But eventually, these pairs, the electrons and holes, start to disappear until you're left with just the baseline electrons and holes. Right, the N0 and the P0. All the excess ones are disappear like so here. So over time it looks like this, and then if you plot it out, the excess carrier concentration versus time, you get sigma N0 at the beginning. So this is what you initially had. Notice that this sigma N0 refers to the same thing as this. Okay, that's the amount, the excess that was generated by the light. So that's your initial amount, and then it decays exponentially with time when you turn the light off. So the equation for that is sigma n, this is the excess carrier concentration as a function of time, is equal to sigma n0, which is the initial amount, e to the negative t over tau. Now, you all have seen exponential functions like this all the time. This tau represents a rate constant. Larger tau, smaller tau will look like this. It will decrease very rapidly. And a larger tau will decrease more slowly, a slower decay. All right, that's what happens when the rate constant is on the denominator. It's t over tau. Okay, so this is these are different decay functions as a function of tau. Okay, so the carrier lifetime derivation, we touched on this briefly, but let me just go over it again. So we define this sigma n of t as a number of excess carriers at a time t. So what we're doing here is we are basically going to derive this equation very quickly. What this is, as we saw with the Schrodinger equation and many other equations that you'll see in this class, it ends up being a differential equation. All right, and it's a statement of conservation of charge. So d sigma n of t dt is equal to the generation rate minus the recombination rate. So what this means physically, this is the excess carrier concentration, the rate of change of excess carrier concentration. How quickly it's changing. It's the generation rate minus the recombination rate. So think about the generation rate as the number of charges that you're putting into the system. That's how many are being generated. And the recombination rate is how quickly you're taking those charges out. And think about a bucket of water. I'll talk about this more when we talk about the continuity equation, but imagine a bucket of water. There's a rate of water going into the bucket, and then there's a rate that you're removing water from the bucket. Okay? The rate of change of water in the bucket is equal to the rate in minus the rate out. All right? So there's the same thing here with carriers. We're just talking about carriers instead of water. Generation rate is the amount of carriers that are being put into this specific space, this specific point in the semiconductor, and the Ri is the recombination rate, how quickly they're disappearing. At equilibrium, remember that the generation rate and recombination rate are equal to one another. So this becomes 0. Right? But this is not an equilibrium case. This is the transient situation. In the transient situation, you have this equation, d sigma n of t dt is equal to alpha r times ni squared. This is the equation for the recombination rate. And it's the equation for the generation rate. The recombination rate is equal to an equation that's slightly different. Okay, notice that when we talked about equilibrium conditions, the recombination rate was also equal to alpha r times ni squared. But in this case, where there are excess carriers, the recombination rate is equal to alpha r times this quantity, NO plus sigma n of t, and PO plus sigma p of t. So what do these things physically mean? This is the total electron concentration, and this is the total hole concentration. All right, think about intuitively why this makes sense. Recombination, as I said, the more holes, the more electrons you have, the higher the likelihood that they'll collide with one another and annihilate one another. So the recombination rate should be proportional to the electron and hole concentration. So that's essentially what this is here. This is the electron concentration, this is the hole concentration. We're including the excess carriers, and then we're multiplying that by alpha r. All right, so this is where the differential equation comes from. Now, if we solve it, we are not going to look at the mathematics of how this equation is solved. I will just tell you that there is a relatively simple solution, as you can see here. The equation is just the exponential function that we saw earlier. You solve the differential equation assuming you have an extrinsic, a doped semiconductor that's either p-type or n-type. So that means p0 is much greater than n0, or vice versa. So it means you have an extrinsic semiconductor, and it also assumes that you have what's called low-level injection. So low-level injection is, have we defined it yet in this class? Okay. Low-level injection is when you're creating excess carriers, but you're only creating enough such that the minority carrier concentration changes. You're not injecting enough to impact the majority carrier concentration. So let me define that more specifically here. So low level injection is defined as when sigma n is much less than n0, and when sigma p is also less than p0. All right, so what it's saying is that the excess let me cross this out. Actually, the right way to say this here, let me say it. They are both less than the majority carrier concentration. So the majority carrier concentration would be the electron concentration for an N-type semiconductor. It would be the hole concentration for a P-type semiconductor. All right, so just remember that definition of low-level injection. I think that's one of the questions on the homework. Is this an example of low-level injection? If we solve the differential equation under those conditions, we get this equation for the carrier lifetime. So we get that sigma n e to the negative t over tau. And the carrier lifetime is equal to 1 divided by alpha r n0 plus p0. Notice again, think about what carrier lifetime is about. If you have, what happens if your n and p concentrations are large? Okay, if they're large, then the denominator becomes very large, tau n becomes small. That makes sense. The carrier lifetime should get smaller when you have more electrons and holes, because there's more likelihood that they'll bump into each other. So this is carrier lifetime. We had an example of majority and minority carrier concentrations due to an instantaneous pulse. So let's see, we can do an example, or you can just see the results of an example of that. So this example, we have a p-type gallium arsenide semiconductor with 10 to the 6th doping, is doped with p equals 10 to the 5th of acceptors, so it's p-type. The concentration of electrons is Ni squared over P0. Let's see, maybe it's good if we go over this problem in class. Let's see if we can just do this real quick. All right, so let's say p-type gallium arsenide. So what you'd typically be given is at the doping, you'd be given the doping levels. So it's doped with Na equals 10 to the 15th per centimeter cubed. All right, so I would give you the doping in a typical problem. And Ni is given to you also. That's a constant for gallium arsenide. The Ni for gallium arsenide is 10 to the 6th per centimeter cubed. What do you notice of the Ni of gallium arsenide versus silicon? It's much smaller, yeah. Does anyone remember the Ni for silicon off the top of their head? It's okay if you don't. 1.5 times 10 to the 10. Yeah, exactly. Trevor's been doing his homework, so it's all in his head now. Thank you. So 1.5 times 10 to the 10 is the intrinsic carrier concentration for silicon. For gallium arsenide, it is 4 orders of magnitude lower. Without looking at your books, which material do you think has a larger band gap? So to think about this, like think about how band gap is related to intrinsic carrier concentration. How would it affect intrinsic carrier concentration?
The larger the band gap, the lower the intrinsic carrier concentration.
You got it. The larger the band gap, the lower the intrinsic carrier concentration, right? So gallium arsenide has a much lower intrinsic carrier concentration than silicon. It's because it has a larger band gap. I forget what the band gap of gallium arsenide is off the top of my head, but I know silicon is about 1.1 electron volts. I think I'm just guessing that it might be like around 1.5 to 2 electron volts. It's written down in the notes somewhere. The actual number isn't important, just so you know that the gallium arsenide has a larger band gap. Let's see. So Ni equals 10 to the 6th. So
1
It's 1.4. Okay, 1.4 electron volts. Thank you. So the electron concentration here is going to be Ni squared over over P0. This is our P0. Okay, so this is 10 to the 6th squared divided by 10 to the 15th. And this comes out to 10 to the negative 3 per centimeter. So this is a crazy low electron concentration. We're in the negatives, 10 to the negative 3 per centimeter cubed. That means that it would take 1,000 centimeters cubed before we could see just a single electron. Okay, it's an extremely low electron concentration. I'm sorry?
We consider this low injection?
I'll get to low-level injection in a second. Good question. So this is a p-type gallium arsenide, so you can clearly see that the P concentration, the whole concentration is 10 to the 15th. The electron concentration is 10 to the negative 3, so this is obviously the majority. It's the majority carrier, and this is the minority carrier. All right. So we've established the baseline. These are the hole and electron concentrations before light is added. And now we do a pulse of light that creates 10 to the 14th electron hole pairs per centimeter cubed at time equals 0. All right, this isn't, by the way, this is a slight difference. This is not giving you any kind of generation rate. This is actually giving you the excess electron concentration. So this is your sigma n and sigma p. It's actually just giving this to you. We don't need to calculate the excess. We're just being given. So the question is, what is the electron and hole concentration versus time? Because this is a pulse of light. The pulse of light immediately turns on and turns off. And so after time equals 0, what happens to the carrier concentration? That's what's shown here. Now keep in mind that this is shown on a log scale. So log scale. Okay, so don't get confused by that. So what we're seeing here are the decays, or the carrier concentration. Sorry, what we're seeing here is the hole concentration. This is the hole concentration, and then this is the electron concentration here. And so this is a log scale. You know, this is 10 to the 12th, 10 to the 13th, 14th, and 15th. And then this is time on the x-axis. All right. So when you take, when you have an exponential function, by the way, just to remind you all, if this is time and then this is, let's say this is x of t, or let's call it y of t. If this is a linear scale, an exponential function looks like that. So let's say y equals k times e to the negative t over tau. Exponential function looks like this. If you plot the exponential function on a log scale, so you take the y-axis becomes a log scale. So let's see what happens when you take the log of an exponential. So you say log y equals log of k times, need more room here. Let's do ln of y equals ln of k times e to the negative t over tau. By the way, I'm using a natural log instead of log. Both are equivalent. I mean, they can be used to show this point. So if you take the natural log of that, you get the natural log of k plus the natural log of e to the negative t over tau. And when you take the log of an exponential, what do you get? Yeah, you just get ln of k minus t over tau. So this exponential curve, which looks like this, curved line in a linear scale, in a log scale, it looks like this. This is ln. If you plot it on a natural logarithm scale, if you do it on a log base 10 scale, it's similar. So that's why these logarithmic functions, the same logarithmic functions that we saw here, this is the carrier lifetime. It's an exponential function. When you take an exponential function, you plot it out on a log scale, they look like straight lines. All right, so this is the minority carrier concentration. This is the majority carrier concentration. So what we notice is that the majority carrier concentration, it decays to 10 to the 15th. That's what we expect. Remember that the whole concentration before the light was turned on was 10 to the 15th. So the light creates a little bit of excess, and then it decays down to 10 to the 15th. All right. So initially, the initial concentration of holes is the amount before the light was turned on plus the sigma n. So let's write this out. P is equal to P0 plus sigma n. So it's equal to 10 to the 15th plus 10 to the 14th. So what does that give you? 10 to the 15th plus 10 to the 14th.
1.1 times 10 to the 15th.
1.1 times 10 to the 15th. So at time equals 0, when this flash of light created these extra electron hole pairs, the initial concentration is 1.1 times 10 to the 15th per centimeter cubed. And you can see that it decays down to 10 to the 15th as the excess carriers go away. So what was the percentage change in this case? From the baseline value to when we turned on the light, how much change did we get in the carrier concentration? 10%, right? So this was a 10% change. All right. Let's look at the minority carrier concentration now. N is equal to, so this is the N at time equals 0. So we'll just put a 0 here. N of 0 equals P0 plus sigma N. So this is, oh, I'm sorry, not P0. This should be N0. N0 plus sigma N. So this is 10 to the negative 3 plus 10 to the 14th. What happens when you add 10 to the negative 3 plus 10 to the 14th?
Yeah, 10 to the 14th.
Yeah, this is approximately 10 to the 14th. The first term is just negligible. So many orders of magnitude lower than that. All right, so that's what's being shown here. It's initially is 10 to the 14th, and it dies down exponentially until it gets down all the way down to 10 to the negative 3. We can't even see it on this plot. So it would just keep on going down to 10 to the negative 3. What's the percentage change here? Initially, the electron concentration is 10 to the 14th. Before we turned the light on, it was 10 to the negative 3. So how many fold increase was it?
17 orders of magnitude.
Yeah, something like 17 orders of magnitude. So 17, so 10 to the 17th increase, 10 to the 17th fold increase in minority carriers. All right. So there's only a 10% change in the majority carriers, but there is a 10 to the 17th fold increase in minority carriers. So the fractional change is very large in the minority carrier concentration. When we define like this concept of low-level injection, this is how we define it. We say that the majority carrier concentration can only change by as much as 10%, not more than that. So this would be an example of low-level injection because the majority carrier concentration is changing by 10% or less. Minority carrier concentration can change very, very significantly. So an example of majority carrier concentration, carrier injection would be if we change this 10 to the 14th and we made this, let's say, 10 to the 16th or 17th. Now the excess carrier concentration is much greater than the initial majority carrier concentration, and that's no longer low-level injection. Any questions? Okay. This is just a little bit about Quasi Fermi-levels. This is a tool, an energy band diagram tool that can help you see the excess carrier concentrations in a diagram. So in the last module, what you did was you had some problems where I gave you the concentrations, I gave you the electron and hole concentrations, asked you to draw the energy band diagram, and then in other problems I gave you the energy band diagram, and I asked you to figure out the electron and hole concentrations. The same can be applied to the Quasi Fermi-levels. Quasi Fermi-levels are used to indicate the electron and hole concentrations in a material when they are under this excess stimulation. So there's excess carriers, excess electrons and holes in there. So this is the equation. You'll notice that it's very similar to the regular Fermi-level equation. The electron concentration, this is the total electron concentration, is equal to Ni times e to the Fn minus Ei divided by Kt. And P is equal to Ni exponential of Ei minus Fp divided by Kt. So Fn and Fp, these are your quasi Fermi levels. And then this N and P, these are the total electron and hole concentrations. So remember that the total N is equal to N0 plus sigma N, and then P is equal to P0 plus sigma P. Okay, so using this equation, you can create energy band diagrams with these new things called Quasi Fermi-levels. And these Quasi Fermi-levels will give you a visual indication of what the concentration is. I think we'll just do this one as have this one as a homework problem that you can work on. From the previous example, I would like for you to draw the energy band diagram and show the original Fermi level before irradiation, and then draw the Quasi Fermi level Fn and Fp after irradiation. Yeah, I'll just let you do that as a homework problem. It's pretty easy. Okay, quick note about an application. One of the useful applications of semiconductor devices, silicon devices, are photoconductors. So a photoconductor is a type of, I guess you could call it a resistor, where the resistance changes with light. So what's going to happen to the resistance if you shine light on a semiconductor? Is it going to go up or is it going to go down?
It's going to go
Down.
I heard up and down. So let's hear your thoughts then. So why do you think it will go down?
Down because like we create more carriers, so we increase the conductivity.
Yeah.
So
Yeah.
the resistance will go down.
That's right. So more carriers, more carriers means more conductive material. So the resistance would go down. So we've also seen that different semiconductors require different wavelengths of light to generate electron-hole pairs. So that's just something that you need to know about photoconductors, that the wavelength of the incoming light has to be greater than the band gap in order for the photoconductor to work. So what we can do at this point, using the stuff that we've learned so far, is we can calculate the conductivity of a photoconductor as a function of the excess electron and hole concentration. So let's see how this looks like. Remember the equation before with no light, the conductivity of a semiconductor material is Q mu n times n plus Q mu p times p. This first term is the conductivity due to electrons. The second term is the conductivity due to holes. And if you just bring the Q out, then you're left with Q mu n times n plus mu p times p. So this is the conductivity of a semiconductor that has no light shining on it. When you shine light on the material, all that's happening is that this n and p are changing. You're creating additional carriers, and when you create the additional carriers, the sigma is obviously going to go up. So this is the equation for it. The sigma is equal to Q times mu n, and all that's changed is that this n has now become n0 plus sigma n. So you're taking into account the electrons due to doping, and then the excess due to the light being shined on the material. Similarly with mu p, this is the initial hole concentration, and sigma p is the additional holes that are put into the material due to the light. And the way that you calculate sigma n and sigma p are the same as before. Sigma n is equal to tau n times GOP. Sigma p is equal to tau p times GOP. All right. In the previous example, without doing too much math, you could do this in your head, actually. How much did the conductivity of the material in the previous problem change?
About 10%.
About 10%, yeah. You have to think about this one. Think about what's going on here. This is good, great. So sigma is equal to Q times mu n times n0 plus sigma n mu p, p0 plus sigma p. What changed here? We started off here when we didn't shine light on the material. When we shine light on the material, in the last problem, what happened is that we said that the hole concentration increased by roughly 10%. So this P went up by 10%. All right, so the second term increased by 10%. The first term, it went up by, it went up by 17 orders of magnitude.
Yeah.
So when we plug this into the equation, let's look at this closer. Maybe this will make more sense. After we plugged this into the equation, n0 plus sigma n, this n0 was pretty insignificant compared to the sigma n, right? Sigma n was something like 10 to the 14th, and n0 was 10 to the negative 3. So the conductivity due to the minority carrier changed quite a bit. It changed to approximately 10 to the 14th. And then the majority carrier term, this one changed also by a factor of about 10%. But when you look at the magnitudes of these two terms, now they are actually almost comparable. This is still about an order of magnitude larger than this term here, right? Because this is being multiplied by let me get that right. This was about 10 to the 14th. This is about 1.1 times 10 to the 15th. So this term is still larger than this one. The conductivity is still being determined by this term. So it's roughly, the change in the conductivity is only about roughly 10, maybe 20%. So not too much. If you did majority level injection, not low level injection, if you did high level injection, I'm sorry, the term I said was majority injection, that's not right. If you use high level injection instead of low level injection, then your photoconductivities can actually change more than 10%. It could change by an order of magnitude, a few orders of magnitude. But in low level injection, the conductivity won't change too much. So some applications of photoconductors are very, very common. In the older type Mission Impossible or Ocean's 11 type security systems, the ones they had in the casinos, where the guy did all the acrobatics to avoid the lasers. That's not how real security systems are done nowadays. I mean, a simple motion detector could have detected them, but hey, it's a movie, But in some of these old school security systems, what they did is they had a laser. So they have so you have the laser coming in this way. It bounces off a material, and then there's a path here, and then here there's a this is a photoconductor. All right, and this is a circuit that measures. What does it measure?
Resistance.
Yeah. By the way, does anyone know what kind of circuit? This is just trivia, but does anyone know what kind of circuit is used to measure resistance? I'll just draw it here just for fun. Something called a Wheatstone bridge. It looks like this. So you make these four resistances approximately equal to each other. And one of these resistances is the resistance that changes. That's what that little arrow is through there. That means that resistance is changing. This means your photoconductor would be part of this circuit. Your photoconductor. Again, you don't need to know this for a test. But you measure this output voltage between this node and this node. And if these two resistances are the same, if the two bottom resistances are the same, then and these two are also the same, the top two are the same, then your V out is going to be 0. But that's how you initially set up the system. But when this photoconductor changes, then your output voltage changes. Okay, that's about the circuit. You don't need to know that. But this thing on the left, this diagram on the left here, this I would expect you to know. So if some person is just hanging out here and blocks the light, what's going to happen to the resistance of the photoconductor?
Go up.
So you took away the light. So what happened to the carriers in the semiconductor? They decrease. That's right. So if they decrease, what happens to the resistance? It increases. Yeah, you got it. And vice versa. So using simple photoconductors, you can detect if someone blocks the path of light, and so hence you have a basic little security system. A more common use of this nowadays is the exposure meters for cameras. If any of you do SLR photography, you go. There is a sensor in there that tells you, a light sensor that tells the camera how long to turn on the exposure for. So when you do photography, you have to open up this thing called the shutter for a certain amount of time. If you're in a low light situation, you have to open up the shutter for a long period of time. And if you're in a high light, like outside on a sunny day, you only want to open the shutter for a very short period of time. So there are photoconductors that are used as exposure meters in these types of cameras. And then the simplest example of all, which has been around for decades, is these night lights. Like you plug them in. They're designed to turn on. They're designed to turn on at night when there's low light, and they turn off during the daytime. So these are all photoconductors that are used to sense the amount of light.
So this is the flashlight this is when we pick the flash when it's dark. This is the same.
Oh, the night lights, you mean? The night lights are the ones that you plug into the wall.
I think she's talking about the camera.
Yeah, the camera.
Oh, you're talking about the camera. Sorry. What about the camera?
Yeah, is it the flash when we turn the flash on when it's dark? Is it like it gives a pulse of, or no?
The flash is different, but the exposure meter tells the camera whether a flash is necessary or not. The exposure meter is basically it could be some type of photoconductor, and depending on the resistance of that photoconductor, you can kind of get an idea of how much light is in the room. If there's low light, then you turn on the flash, or you do a long exposure. And if there's a lot of light in the room, then you don't use the flash and use a short exposure time. So semiconductors are really good as light sensors. Another example of, this is photodiodes are actually used in this application, but I'll just mention that a really important application of semiconductors as light sensors is in fiber optic communications. We are sending like terabytes or exabytes of data across our fiber optic cables that run from city to city. They run from continent to continent. Did you know that there's undersea cables, undersea fiber optic cables that go under through the bottom of the Atlantic, and they connect us to Europe?
The bottom of the sea.
Yeah.
Or are they suspended?
No, as far as I know, they're actually at the bottom.
That's very
miles and miles and miles of it. And I read an article recently saying that the U.S. was a little bit worried that they were tracking Russian subs that were near the fiber optic cable. And tell you, if you want to destroy the U.S., just cut off the Facebook, and people will go nuts. No, but I mean, I'm sure you all know that if we don't have fiber optic communications with continent to continent, like our whole society breaks down. So. Anyway, that's very important, I guess you could say. All right, let's move on to carrier diffusion. I like showing this video. This video is on chemical diffusion. I guess it's not available there. Okay, so let's look at let's see a different one. Right. Chemical diffusion. If that video is not there, I'm sure we can find another one. Nice. Nice. Okay, I was looking for that video, but I couldn't find it. Anyway, I mean, if you look at this example here, what happens if you take a drop of food coloring, you put it in water. That food coloring spreads out over time, right? That's diffusion. At the chemical level, what's happening is that the molecules are going from high concentration to low concentration. Right? Molecules, objects, they just naturally do that. They go from high concentration to low concentration. And, the carriers are no different. If you have a high concentration of carriers in any given region and a lower concentration like nearby, then there's a gradient, a concentration gradient. So that means that the carriers will diffuse from high to low concentration. In a semiconductor, diffusion will occur if there's a gradient of carriers. But when we say gradient of carriers, we just mean to say that there's a region of high concentration and then there's a region of low concentration near each other. The speed of diffusion is proportional to the concentration gradient. So if you have really, really high concentration here and really, really low concentration right next to it, there's going to be rapid diffusion from high to low. On the other hand, if the two concentrations are not so different, if they're just slightly different, then the rate of diffusion is going to be slow. That is Fick's law. We'll look at an equation for that. So, if we wanted to create a carrier, if we wanted to make a concentration gradient in the chemical world, very easy. You just take a bowl of water and you drop some food coloring in the middle, and boom, you have your concentration gradient. Right? High concentration where you drop that food dye, and then low concentration everywhere else in the bowl. With semiconductors, the way that we do that is that we use light to irradiate the material locally. So let's say we have a block of semiconductor material, and then we just irradiate the middle of the semiconductor with light. So you're going to create a lot of carriers in the middle, high concentration at that point, lower concentrations on the outside, and you'll generate a gradient. And so where are the carriers going to diffuse? How are the carriers going to diffuse?
To the right and to the left.
Yeah, away from the light source. Exactly. So this is a qualitative example of it. So we have a pulse of light incident at t equals 0. And so you imagine that there's a light at t equals 0. Okay, and right where you created, where the light is going through the material, that's where you create the carriers. All right, so you created all these carriers by turning on the light. I'm just going to go back here. When you turn the light on, the carriers get created instantaneously, and then you turn the light off. All right, and you have these carriers in the middle, and they're still left there. The excess carriers still remain. So the blue is the electrons, the white are the holes. And if we were to plot the excess carrier concentration, actually this one is just showing the electron concentration here, n of x, it would follow this type of Gaussian profile. All right, a sharp peak in the middle, and then it decays down on both sides. So it actually looks like a Gaussian, a bell-shaped function. All right, it's not a square wave. All right, if there was a square wave, that would imply that there's an infinite concentration gradient. Let's talk about why that means. This is carrier concentration, right? So the slope of this line is equal to dn dx, and this is the concentration gradient. This is concentration, this is space. All right, you have a bell-shaped curve here like this. The slope of this line, dn dx, is the concentration gradient. All right, now the more the concentration gradient, the faster the diffusion. If we happen to have, hypothetically, if we just had a square wave that looked like that, that would mean that we have an infinite concentration gradient, and that doesn't actually happen. These things, or even if it does, it's there for a very, very short period of time. Let me delete that. Erase. Okay. So when we turn off the laser, now we're at time 1, and you can see a bell-shaped curve. like this, the carriers diffuse outwards. And so you imagine the carriers just moving out like this. At time equals 2, it's the electron concentration versus space looks like this. It's still a bell curve, but it's fatter and shorter. At time 3, it goes on to something that looks something like this. The carriers are spread out more, so the curve is even wider, it's even fatter, and it's shorter again. Right, this is just because the carriers are spreading out over time. If you want to look at this mathematically, well, pseudo-mathematically, think about this, is that you have at time 1, now you have a very sharp concentration gradient. It's super high concentration in the middle and almost no concentration on the outsides. Your excess carrier concentration on the outsides are 0. And you have a super high excess carrier concentration right in the middle. So there's a very sharp gradient here. So initially, the carriers diffuse out very, very rapidly. So this happens very quickly. And then now that these carriers are more spread out, there's less of a concentration gradient. They'll still diffuse, but they do so at a slower rate. Right? That's what happens at T3. So if you want to look at it mathematically, again, think about the slopes. Here, there's a sharp concentration gradient. The slope here is large. At T2, the carriers are more spread out. The slope here is more gradual. And T3, the slope is even more gradual. So the concentration gradient gets smaller and smaller with time. So this is an example that's carrier diffusion due to an instantaneous pulse of light. At T equals 0, then you turn it off and you let the carriers diffuse. We'll revisit this again when we talk about the Shockley experiment. It's a way to measure the mobility and diffusion coefficient in semiconductors. All right, so here are some equations that are governing carrier diffusion. I added this chart here. You can draw this in if you like. It's just to visualize this. This is from one of the textbooks. So the equations that govern carrier diffusion is similar to something called Fick's law. Fick's law governs chemical diffusion. And you could say that this is a form of Fick's law that governs the diffusion of carriers in a semiconductor. So mathematically, what's being said here is that the diffusion current, Jn diffusion, so this is the diffusion current density due to electrons. J, if you remember, is current density, and the units for current density is not amps. It's not amps. It's amps per centimeter squared. We talked about that when we were talking about drift currents. So J means current density. N means we're dealing with electrons, so the electron current density. And diff means it's due to diffusion. Jn diff is equal to Q, which is the constant 1.6 times 10 to the negative 19. Dn is the diffusion coefficient. Now this is a constant for semiconductors. It's a constant that depends on the semiconductor that you're working with. In general, like semiconductors that have high mobility will also have high diffusion coefficients. And there's a relation between the two called the Einstein equation, which we'll talk about a few slides forward. So Q times D sub n, this is the diffusion coefficient. You can look this up in a chart. And dn of x dx. So this is the concentration gradient. dn of x dx is the concentration gradient. This is a constant. This is a constant. All right, so let's qualitatively look at what this means. This is saying that the magnitude of the diffusion current is going to be proportional to dn of x dx, which is the slope. So I say this is, let's say this is x, and this is n of x. So this blue line is just illustrating a concentration gradient for electrons. So this side here, this is low electron concentration. This side here is high electron concentration. All right, the slope dn of x dx. So that's the slope there. The slope is a concentration gradient, and this equation is simply saying that the current is proportional to this slope. So, for example, if this were super steep like this, if this blue line happened to be super steep like this, then you would have a higher diffusion current. All right, so let me just erase that. Okay. Now, the second thing I want to point out is about the signs. Okay. In this case, when you have a low concentration on the left side, high concentration on the right side, the electron flux is going to go from right to left. Electron flux means like the direction that the electrons are moving. Electrons are always diffused from high to low. Holes also diffuse from high to low. Everything, all the carriers diffuse from high to low. So imagine the electrons moving from right to left. And when they move from right to left, the current is going to go in the opposite direction. Does anyone remember why that is? When electrons move one direction, the current is in the opposite direction.
Because electron leaves the hole. It's all movement.
It's it's actually a simpler answer than that. I mean, we define the way that electricity is defined. We define it as a movement of positive charge. So the way that we define current is the movement of positive charge. So whatever directions the electrons are moving, the positive current is going in the opposite direction. And I think what you said, it makes sense, right? Like you're talking about what's happening at the semiconductor level. Electrons moving in one direction, the empty states moving in the other, the holes moving in the opposite direction. So that's a valid answer. So if the electrons are moving from right to left, the current, as we define it, is moving from left to right. So the diffusion current here in this case is positive. Right? That's why there's no sign here. By contrast, if we have the same situation with holes, all right, let's say we have a low hole concentration on this side, a high hole concentration on this side. The holes are diffusing from right to left. Does everyone see that? They're diffusing from high to low concentration. Okay, so the holes are moving this way. When the holes are moving in a certain direction, which they have positive charge, the associated current is also moving in the same direction. So in this case, the diffusion current is moving from right to left. So right to left means it has a negative sign. That's where this negative sign comes from. So it's important to not mix up the signs there. They're very important. So I think we've covered that. So this is Fick's law. These are the equations governing diffusion currents. I forgot to mention that the diffusion coefficient D depends on temperature and also depends to a lesser extent on doping conditions. So just keep that in mind. All right. So these are examples where the electrons and holes are moving due to a concentration gradient. The other way that we learned in the last module how they can move is in response to an electric field. What type of movement is that called? Close, yeah, drift, exactly. So this is diffusion current. The other one is drift current. So now that we're at this point, we can summarize the four processes of the carrier life cycle. We talked about this at the beginning of the module. I didn't have any of the equations there, and now, by now you have equations for each one of these, so you can understand more quantitatively what the carriers are doing. So there's carrier generation. An electron and hole is generated via thermal, optical, or other means. This equation happens to apply just to equilibrium, so just keep that in mind. Gi equals Ri equals alpha R times Ni squared. This is generation at equilibrium. after the carrier is generated, it can move in one of two ways. If there is an electric field present, then it would drift. And drift current is governed by this equation. So the current density, J sub n, so this is the current density of electrons, and we don't have anything else at the end there indicating drift. We could indicate drift if we wanted to, or we just leave it blank and drift is assumed. Jn equals the electric field times the conductivity, sigma sub n. So this, and sigma n is q mu n times n. Similarly, Jp is equal to E times sigma p, which is equal to E times Q times mu p times p. I'll add those in there just so you have it. E Q times mu n times n. E Q mu p times p. All right. So mobility is related to drift current. All right, drift current is proportional to the electric field that you apply. It's also proportional to the mobility. It's also proportional to the electron concentration. Compare that to diffusion, which we just noted, is that diffusion is when an electron or hole moves due to a concentration gradient rather than an electric field. And the equation for that is Q times dN dx. This is the electron diffusion current, and similarly for holes. What you notice if you compare the two is that drift current is proportional to the electron concentration, and diffusion current is proportional to the gradient, exactly, the rate of change of electron concentration. So that's one important point. The second important point is the constant. Jn, the drift current, is dependent on this constant of mobility. And the diffusion current is dependent on this constant d sub n, which is the diffusion coefficient. And then we both have Q in the terms also. All right, so they're both fairly simple equations, and you can see how they relate to one another. Now, I just want to point out that drift and diffusion can actually happen at the same time. You know, the way this flowchart is, you might get confused and think that it's only one or the other. That's not true. They can both be happening simultaneously. In fact, a carrier could be impacted by diffusion and drift at the same time. Because if you have a concentration gradient that exists and you have an electric field and a voltage that's being applied to it, then both situations are happening. And that's what happens in diodes. We'll talk about diodes in the next module. All right, so now that we know that diffusion and drift can both exist, we have to combine them together. So you think about the total current in a semiconductor, we have to consider both diffusion and drift components due to electrons and holes. So there's a total of 4 different components, as we saw in this previous slide. There's drift due to electrons, drift due to holes. Diffusion of electrons, diffusion of holes. 4 different components. And when we add those up, that's what we get here. This is the total electron current, is the current due to drift, the current due to diffusion. The whole components are given here, the total due to drift, the total due to diffusion. And then the grand total is when we add up all 4 components together. All right. And just one point here, remember the signs that when you, in your diffusion equations, the whole diffusion equation has a negative sign in it. And that's something that sometimes trips up students. All right, so all we're doing is we're combining everything together now to get a more comprehensive model. Let's see. I think we can skip. Oh, let's just do this real quick. I think, you know, we did something very similar to this, but it doesn't hurt to just do it again real quick. Suppose we have an electric field with the concentration gradients as shown. So we're going to draw an arrow to indicate the flux, the direction that the electrons or holes move. due to drift and diffusion, and then draw an arrow indicating the direction of the current due to each mechanism. So let's start with number 1 first. So this is what we're showing. The electric field is moving from left to right, and the concentration of electrons is going down as we go from left to right. The concentration of holes is going down as we go from left to right. All right, so we can just do this together as a class. We want to draw an arrow indicating the flux of the electron. So the electrons, due to drift, okay, there's an electric field, so the electrons are drifting. Which way do the electrons drift?
High concentration to low concentration. Right.
That's diffusion. We'll get to diffusion in just a second. Right now we're just talking about drift.
Direction of the current.
Opposite,
Electric field.
opposite the electric field. Yes. When we're talking about drift current, we look at the electric field. So the electric field is pointed from left to right. Electrons always move opposite the electric field. So the electron flux is from right to left. And how about the holes for the drift current?
With the electric field.
It goes in the same direction, correct. Same direction as the electric field, so the holes are drifting from left to right. How about diffusion? Diffusion is determined by concentration gradients, right?
Left to right.
Is the current direction and the flux direction be the same?
Not for electrons, they're going to be opposite.
So in the first question, they're asking about the arrow for the flux. The second question is for the current.
The second question is the current, yeah. The first one, in the first question, we are just considering which direction the electrons and holes are moving. Yeah, good question, good question. So for diffusion, which way are the electrons diffusing?
Left to right.
Left to right. Why is that?
High to low.
High to low concentration, right. High to low concentration. And how about the holes?
The same.
Same thing. Holes are diffusing from left to right, high to low concentration. Good. Now, draw an arrow indicating the direction of current due to each mechanism. All right. So we look at this chart here. We say, well, the electrons, due to drift, they were moving from right to left. They were moving opposite the electric field. And what is the current resulting from that? So if electrons are moving from right to left,
Left to right.
the current is left to right. The current is in the opposite direction. Okay, now you have holes that are drifting from left to right. What is the corresponding current?
The same.
Left to right.
Left to right. One thing I want to point out here, notice that the current, the drift current due to electrons and holes, they're in the same direction. That makes sense, right? If you put an electric field across the material, the drift currents they're in the same direction. If the electrons and holes were fighting against each other, then you wouldn't end up, then you wouldn't really have drift current. So the drift current can be due to electrons and holes, that the currents are always in the same direction. The electrons and holes are moving in opposite directions, but the currents are the same, in the same direction. All right, now the diffusion currents. So we know that the electrons are diffusing from left to right. So the associated current would
Right to left.
right to left. Yep, you got it. And in the case of holes, the holes are diffusing from left to right.
Right to left.
Left to right.
Yeah, the diffusion currents are in the same direction as the movement of the holes. So wherever you have holes, notice if you just look at the bottom line here, whatever direction of the arrow is for holes, the associated currents are the same direction. And for the electrons, it's the exact opposite direction. All right, so when you have a concentration gradient like this, you end up having these very interesting current pattern. The drift currents, 3 of the drift currents are going in one direction, and 1 of the diffusion currents is going in the opposite direction. So you can actually have situations like this when you do non-uniform doping profiles. So let's say you have like an N-type semiconductor on one side, and then you, instead of doping it uniformly, you dope it, you have a doping gradient. So it's gradually changing from n-type to p-type. Then you'll have all sorts of interesting things happening when you change the doping. In fact, what we're going to look at in the next module is the diode. A diode is simply a p-type material and an n-type material right next to each other. It's an abrupt junction. There's a sudden, it changes suddenly from p-type to n-type material. And so you get these drift and diffusion currents that end up canceling each other out, and that's responsible for a lot of the very unique properties of the diode. We'll find that out in the next module. All right, so quick discussion question. Suppose we place an electric field over the length of a semiconductor. Which carrier contributes more to drift current? Majority or minority carrier? If we place an electric field over the length of a semiconductor. Majority carrier, okay, why is that?
Drift current is basically from positive to negative.
Positive and negative, right? But this is asking about the majority or minority carrier. Well, you're correct in that the majority carrier does contribute more to the drift current.
Is it just because the majority carrier moves more charge?
The majority carrier moves more charge. Yep, that's right. We could show this mathematically. You know, Jn. Remember these equations? Jn is equal to E times sigma n. So Jn drift is equal to E times sigma n is equal to E times Q times mu n times n. And the whole current is equal to E sigma p is equal to the electric field times Q times mu p times p. Now, whichever one of these is present at a much higher concentration is the majority carrier. The total current is equal to E times Q times, mu n times n. This is the contribution of electrons, and the second term is the concentration of holes. The question is asking which carrier contributes more to the drift current. And so if the electrons are the majority carrier, the electron concentration is going to be much larger than the hole concentration, right? So in that case, the electrons are going to contribute much more. This term is going to be much more dominant than the second term. And vice versa. If it's a p-type semiconductor, P is going to be much larger than N. So the P is going to contribute more to the current than the N. So the majority carrier contributes more to drift current. Second question is, suppose we create a gradient of carriers by irradiating the sample with light. Which carrier contributes more to the diffusion current?
Majority. But they have to move from the high concentration to the low concentration.
Okay, let's look at that. So the Jn, the diffusion current, is equal to Q times d sub n dn dx. And the whole current due to diffusion is equal to negative Q times d sub p dp dx. All right, now suppose we have some type of concentration gradient here. Let's say this is showing the n of x. Sigma n of x. Let's see. So sigma n of x. And remember, that's equal to sigma p of x. When we say we irradiated the sample, we create electrons and holes in pairs. So whatever the sigma n of x is, the sigma p of x is going to be the same. And this is versus time. Or, I'm sorry, this is versus space. We're irradiating a part of it, the semiconductor, and we're leaving the rest of it be blank. Here, let me just sure this is clean. All right, so let's take a closer look at this. Q d sub n d sigma n x dx. All right, what do you notice here? What do you notice about sigma n of x and sigma p of x? So these two things.
They should be equal.
They're the same, yeah. They're equal to each other because you're creating them in pairs, right? So this sigma n of x and the sigma p of x are actually equal to each other. As a result, these two currents, these two terms are similar. The Q term is identical. So what are you left with? dN and dP. So whichever carrier has the higher diffusion coefficient will generally, have the dominant diffusion current. So that's a tricky question. There's a lot of things to think about there. But the answer here is whichever has the larger diffusion coefficient.
Which is inversely proportional to concentration, right?
The diffusion coefficient?
Yeah.
No, the diffusion coefficient is a constant for a material. So whichever, the diffusion coefficient turns out to be proportional to mobility. We'll show that on the next few slides. But so whichever carrier has a higher mobility is going to have a higher diffusion coefficient. So which of the two carriers has higher mobility? Electrons or holes?
Electrons lighter.
Yes, good. Yeah, you remember. Good. Electrons have a lower effective mass than holes do, so they tend to have a higher mobility. Electrons, we're talking about silicon here, okay? Because most of the stuff we talk about in this class has to do with silicon. Other materials can have different traits, but if electrons have a higher mobility, then they have a higher diffusion coefficient. We'll get to that when we talk about the Einstein relationship. So here's our diffusion and mobility constants for the three most common semiconductor materials. Germanium, silicon, and gallium arsenide. Silicon is obviously by far the most common. Okay. There we go. So silicon has, these are the diffusion coefficients, 35 and 12. This is for electrons and holes. And the units for diffusion coefficient is centimeters squared per second. And the mobilities for silicon is 1350 and 480. This is for low doping concentrations. Okay, normally on an exam, if I give you these constants, remember that these constants are assuming low doping. You guys know that the doping, as you go to high doping levels, the mobility decreases due to
Distance.
well, when you have more impurities.
Ionic
There-
impurities.
Yep, very close. Yep, ionic impurities. What type of scattering does that cause? Let's back up for a second, because I know like these things I think about them automatically, but let's remember to go through it slowly. We're talking about doping. We're talking about the effects of doping. All right. We're talking about mobility. So when we're thinking about mobility, the things you want to think about is like what determines mobility. What determines the mobility of a material?
Carrier concentration.
Well, take a step back. Think about the mechanism of mobility. Mobility has to do with these materials like moving through the electrons and holes moving through the material, right?
While scattering.
Scattering, exactly. So scattering is what determines mobility. What are the two mechanisms of scattering? that we learned about in this class?
Lattice scattering.
Lattice scattering, which depends on what? Lattice scattering depends on temperature, right? You got it. More vibrations, more lattice scattering. The second thing that we talked about was impurity scattering. That's the one, David, you were thinking of. With impurity scattering, that's determined by the dopant ions, right? So what happens if we increase doping?
Mobility decreases.
Right, you get more, if you dope the material more heavily, you get more impurity scattering, and therefore that would reduce your mobility. Okay, so these mobility numbers that are given to you in this chart, they're only for room temperature at low doping concentrations. In an actual exam, you would get that chart, the doping versus mobility chart for silicon. Okay, these are the constants for germanium. And one thing that you can see here is that germanium has a, like 3x higher mobility of electrons than silicon does, and almost a factor of 3 for the holes as well. So germanium is a high mobility material. So there is it's used in high speed electronics. The diffusion coefficients are also larger. Notice that the diffusion coefficients are proportional to mobility. Gallium arsenide is the king in terms of speed of these three materials when you're talking about the electron mobility, 8,500 versus 1350. So you're getting a factor of what? Six or so between the two. So just immediately, just by switching to gallium arsenide, you see that the electrons are moving through the material 6 times faster. That's crazy. That's one of the reasons why gallium arsenide is used for a lot of high-speed devices. When you're building amplifiers, like high-speed amplifiers that are, amplifying like, gigahertz signals from cell phone towers, we can do that stuff in silicon right now because the silicon technology has advanced quite a bit. But before, that stuff used to be done in gallium arsenide. And gallium arsenide is still used today for the really high-speed stuff in the tens or hundreds of gigahertz for some of the military and radar type applications. But interestingly, the whole mobility is not, is actually slower, it's the slowest of the three. It's kind of a lopsided material. It's kind of interesting. All right, so these are the constants for common materials. Now we talk about the Einstein relationship. If you look from this chart, you notice that the diffusion, if a material has a high mobility for electrons, it has a high diffusion coefficient for electrons, and so forth. Basically, the diffusion coefficient and the mobility are proportional to one another. So another way of putting this equation is D equals KT over Q times mu. They're proportional to each other. This is called the Einstein relation. It's an important equation because it allows us to calculate D or mu if the other is known. So on a test, if I give you, or if I tell you to look up the mobility on a chart, from that mobility you should be able to calculate the diffusion coefficient. Or if I give you the diffusion coefficient, you should be able to calculate the mobility. This is a surprisingly simple equation that Einstein derived, that it can be derived from the drift and diffusion relationship, assuming that you don't have current in the semiconductor and assuming that you're at equilibrium. He uses something called the continuity equation, which we'll talk about next, but you don't need to know the derivation of this equation. You only need to know what the result is. I just mentioned this is that the origin is that you set the current. This is the current density due to holes. This is the current due to drift. This is the current due to diffusion. So these two parts you should be familiar with. So you set those two equal to 0. So when we say that there's no current in the semiconductor, we set the drift current and the diffusion current, the sum of the two, equal to 0. And we also assume that we're at equilibrium and the carrier concentrations aren't changing with time. The way that you derive this simple relationship is that you relate this electric field. The electric field is actually related to the concentration gradient. So E and dP dx actually are related to one another through the continuity equation. We'll talk about that next. And using that, you can calculate this relationship. So the way to remember it in your head is d over mu equals kt over q. It kind of rhymes. D over mu equals kt over q. This kt over q, another rule of thumb to remember, is that this is equal to 0.026 volts. Just to remind everyone from the module 2, kT on its own is equal to 0.026 electron volts. kT is a unit of energy. kT over Q turns out that it's a unit of voltage, and it's equal to 0.026 volts at room temperature. So this is, kT is 0.026 eV at room temperature. kT over Q is 0.026 volts at room temperature. Okay. I think that we can get into the continuity equation on Wednesday, because I don't want to start explaining this and then end it 2 minutes later. So let's just stop here for today. The one thing I want to mention about the continuity equation is it's an equation that brings a lot of concepts together. So it brings in drift, diffusion, generation, and recombination, and it's a statement of conservation of charge. The importance of the continuity equation is because this is the equation that's used if you have a device and you want to understand how current flows in the device. This is the kind of like Newton's laws for solid state electronics. So we'll get to that in the next class. So please try your problems that you have on module 4. Since the test is delayed till not next Monday but the following, I still don't want you all to just not do the homework and wait till the last minute. It's better if you do it now. It'll make the rest of this module go smoother for you, and you'll be in much better shape for the test. There is quite a bit of material on the test, so if you do it all at the end, not a good idea. So get started on it. Ask me questions, and then I'll see you on Wednesday. Okay, thank you.